Welcome back, students. In this video segment, we will cover two sections, sections 1.5 and 1.6. Both of these sections involve one topic. The topic is determinants. The second section, section 1.6, is just a list of further properties of determinants, So let's go ahead and get started right off. Okay, first, you have had, most likely, earlier exposures to this thing called a determinant. If you've taken Calculus 3, you've looked at the cross product of vectors. If you haven't taken Calculus 3, some physics courses present the cross product in terms of determinants. In fact, I think that most physics classes do. And even if you haven't taken Calc 3 or any physics, you very likely studied Kramer's rule, which is a method for solving systems of equations in Algebra 2 or in intermediate algebra. And some pre-calculus instructors also review Kramer's rule. So anyway, in this section, in the next section, we take a look at a thorough treatment of determinants. So why do we need to see determinants for a third time? Well, we need to be able to compute determinants of large matrices in STEM field math courses or in STEM field math areas. The determinant holds a lot of the theory of linear algebra together, and you're going to see that very, very soon. We also need efficient methods for computing determinants. The fact is, the computation of the determinants that you did in Algebra 2 or in intermediate algebra or even in Calc 3 were determinants of fairly small matrices, most likely 3 by 3 matrices. Well, the number of operations required to compute determinants for large matrices is huge, is astronomically huge, even for relatively small matrices, even for like 25 by 25 matrices, which in the scheme of things isn't that big. The number of computations is enormous if you use the method that was presented to you in Algebra 2. So we need to look at efficient ways of computing determinants via computers. And this section and the next section does that. We also need to understand the underlying theory behind the computation of determinants, even though most of us in the course are not math majors, so we don't necessarily need to concentrate on the theory. We do need to have understand the underlying theory, primarily because a good number of students who are taking this course are likely to be involved in coding and writing programs for other engineers or other STEM workers. And in order to code the computer or code computer language, an understanding of the theory of how determinants behave or how they're computed needs to be understood. Okay, so with that, let's go ahead and let's study determinants. The first thing I want to do is introduce you to the concept of a miner. Not like a gold miner or someone hasn't turned 18 yet. Miners are certain matrices that are related to other matrices. So let's look at a specific example. Let's let A be the matrix whose entries are very simple. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Tend to recycle this matrix a lot. I'm going to define something called the 1-1 miner of A. Now, that's not the name that this textbook uses. This is a name that I didn't make up. I grabbed this name out of a different textbook. In fact, I think it's the name of the miner this is using the terminology that I grew up with. In any case, we have something called the 1-1 miner of the matrix A. I'll be writing out the the words with this definition in a second. And that is the matrix whose entries, the 2 by 2 matrix whose entries are 5, 6, 8, and 9. Okay. Now the terminology that the author of your textbook uses, which is just fine, is, he says, your author calls this the minor of entry A11 of the matrix A. I use the terminology the 1, 1 minor of A. Absolutely equivalent terminology, or terminology that means exactly the same thing. So for example, if I want to use, or if I want to find the 1, 2 minor of A, the 1, 2 minor of A, that would be 4, 6, 7, and 9. So, going back to the 1, 1 minor of A, the 1, 1 minor of A is the matrix obtained. It's the matrix obtained by deleting the first row and the first column of A. So that sort of reveals how I got the 1, 2 minor of A, or the minor of entry A12 of matrix A, using the terminology of your author. You take, to find the 1, 2 matrix of A, you take and remove the first row and the second column of A. So remove the first row, remove row 1, and remove column 2. Column 2. If you remove row 1, 2, the entries whose entries are 1, 2, and 3, and column 2, whose entries are 2, 5, and 8, you're left with the matrix of size of dimension 1 less than we started. We started with 3 by 3. We end up with a 2 by 2 matrix whose entries are 4, 6, 7, and 9. If you don't get the pattern yet, it's really very simple. You're not going to have a hard time. If I want the 2, 3 minor of A, or using the terminology of your author, the minor of entry A2, 3 of matrix capital A, you remove row 2, 4, 5, and 6, and column 3, 3, 6, and 9, to get the matrix whose entries are 1, 2, 7, and 8. Okay, so I hope that makes sense. 1, 2, 7, and I was making sure that I computed that right. Yeah, it looks pretty good. Okay. So generally, if A is an n by n matrix, if A is an n by n matrix, Mij is the matrix obtained. It's the matrix obtained by removing or deleting row I and column J from A. Okay, and I call it the IJ minor of A, and your author calls it the minor of entry AIJ of A. Okay, don't get too caught up in the difference in the terminology. They mean exactly the same thing. So, without further ado, on to determinants. On to determinants. Let's compute determinants now. So determinants can be thought of as an operation that turns an n by n matrix into a real number. That's really kind of an abstract beginning to this, but it's true. It's an operation that turns a matrix into a real number, into a scalar. So here's how it goes. Let's start with the smallest size matrix possible. Let's let A be a 1 by 1 matrix. So if A is a 1, 1 matrix, then the determinant, and we abbreviate determinant as DET, in parentheses, of A is simply a 1, 1. Okay, that's not real exciting. That would be an easy computation for any computer. So if A, or person, if A is a 2 by 2 matrix, A11, A12, A21, A22, then the determinant of A is A11, A22. This is just a review, and I'm sure you remember this, or if you don't, it's going to come back real soon. Minus A12, A21. So in other words, the determinant of a 2 by 2 matrix, to get the determinant of a 2 by 2 matrix, you multiply the entries along the main diagonal, the forward diagonal, if you will, a downward diagonal, and you subtract the product of the entries in the upward diagonal. Very, very simple stuff. Okay, real simple reminder in terms of example. The determinant of the matrix 1, 2, 3, 4 is nothing more than 1 times 4 minus 2 times 3, or 4 minus 6, which is negative 2. Okay, and now for a little brief notation alert. Notation. There's an alternate notation for the determinants, which you're probably familiar with. We can write, instead of writing DET 1, 2, 3, 4, we can write sort of like extended absolute value signs, form the matrix without completing the brackets. So this sort of putting the matrix between two absolute value signs and removing the brackets is another way of writing the determinant. And we'll go back and forth between notations, and you can too. Okay. So on to the really the purpose of the section is the computation of larger matrices, larger square matrices than 1 by 1 or 2 by 2 matrices. Okay. The example that I'm going to come up with or come up with next is going to be an example of computing a determinant by expansion about the first row. So all of a sudden we get complicated talking, or complicated in our description. This is likely to be what you remember in terms of how to compute the value of a determinant, although in an intermediate algebra course you may not have actually named it this thing. So computing a determinant by expansion about the first row. So let's examine the computation of the determinant of the matrix whose entries are 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. So I'm going to do to help things along and I'm going to introduce a series of alternating signs above the first row. Plus, minus, and plus. Okay. And then what I'm going to do is I'm going to imagine a line through the first row. And that line is going to stay through the first row through the whole process of evaluating this determinant. Okay. And then next I'm going to imagine other lines, vertical lines, going through the columns one at a time. One at a time. So now imagine a vertical line passing through the first column. I'm going to put only a part of it in green, but I'm going to imagine that it passes all the way through. Here, I'll just write it there. The first row. It'll work. Okay. And what happens is you can imagine that horizontal line and the vertical line intersecting at a particular element in the matrix. It also passes through the first plus sign. So you can imagine then that the lines, the horizontal and the vertical green lines, they intersect at plus, little positive red sign, 1, first element in the first row, A11 entry or element. And then we multiply that by the determinant of everything that doesn't have a line through it anymore. So the determinant of the entries 5, 6, 8, and 9. Okay. And this procedure is going to continue. It's got 2 more parts to it. So let's get rid of the vertical line, so that we now move that vertical line over 1 column. So now the vertical line is coming through the second column. Okay, and that vertical line intersects at the first row and second column, so it intersects at the red minus sign. It also intersects at 2 elements in the first row, second column. And then we multiply that by the determinant of everything that doesn't have a line through it. So you can probably see why I started this discussion with the concept of a minor. That's exactly what we're forming here. And then we do this process one more time. I'm going to erase the second, or the line through the second column. And I'm going to place that line now through the third column. Notice that the line through the first row never moves. That's why we call it an expansion of about the first row, because that line never moves through the first row, so we're expanding about that fixed line. The intersection of the vertical line that moved with the horizontal line that doesn't move is at plus, positive sign, so it becomes the operation plus, and the entry 3, and then we multiply that by the determinant of everything that doesn't have a line through it, a little green line through it, namely the 2 by 2 matrix whose entries are 4, 5, 7, and 8. The rest is very simple. The rest, because we already have the definition of the determinant of a 2 by 2 matrix, is extremely simple. We just get 1 times 5 times 9 minus 6 times 8 minus 2 times 4 times 9, multiply the downward diagonal, minus 6 times 7, multiply the upward diagonal, plus 3 times 4 times 8 minus 5 times 7. All right, and I'll skip the rest of the computation. This turns out to be 0, but in a sense this makes my example a very poor one, because the determinant doesn't have to be 0. The determinant can be any real scalar or any scalar. So we just happen to get a determinant here. In our theory coming up, whether the determinant is 0 or a non-zero scalar is gonna have an impact on a lot of that theory. So this is important, but it doesn't always have to equal 0. Okay, so now let's take a much closer look at the evaluation of the determinant of a 3 by 3 matrix by expansion about the first row. So let's do it. Let's compute the value of a determinant of a 3 by 3 matrix by expansion about the first row. So if it helps, and it probably does, let's get that green line through the row about which we're expanding this matrix. So a green line going all the way through the first row, stays fixed there, solid, through the first row. Okay. So a little cat out of the bag information about what's coming up. We can also expand about the second row or third row, or the first column, second row. We can expand about rows and columns, but the really common first way to introduce this to students is by expansion about the first row. So let's do it. Now I'm not going to write the little plus, the little minus, and the little plus in red. I'm going to skip that. I'm going to make this more of a formula. I'm going to include those signs in this formula. So to do this, you can imagine that the little green line through the first column also, intersection is at A11. So remember I said I was removing that little red plus, and I'm going to replace that little red plus with the factor -1 to the 1 plus 1. And the 1 and the 1 and the exponent come from the first row, first column. Then I'm going to multiply by A11. Then I'm going to multiply by the determinant of everything that doesn't have a matrix through it, a line through it. So times the determinant of the matrix whose entries are A22, A23, A32, and A33. Okay, so let's move it along. Plus, the little minus sign, red minus sign, is being replaced with -1 to the, now, to the next part of the process before was to imagine the little green line being moved through the second column. Now we can do that again. So it's going to be -1 raised to the row, first row, 1, plus now second column, times A12, times the determinant of the matrix. The determinant of the matrix is formed by the entries that don't have lines through them anymore. So A21, A23, A31, A33. So you see how this is formed, I think. Okay, I'm going to keep going. Let's take away that green line through the second column. Let's take that little green line, put it through the third column. So, plus the little red plus that I had above the matrix before in the first row and third column is replaced with -1 to the first row, 1 plus third column, times the determinant of everything that doesn't have a line through it. A21, A22, A22, determinant of the matrix that doesn't have, formed by everything that doesn't have a line through it. A31, A32, A31, A32. Okay. Now we bring in the concept of minors. That first matrix we're taking the determinant of, this little guy right here, that was the matrix obtained by removing row 1 and column 1. That was the matrix obtained by removing row 1 and column 1. That is M11. The next matrix over is we removed row 1 and column 2. That's M12. And that last minor is the 1, 3 minor of A. So we can collapse the notation a little to make it a little easier on the eyes, a lot easier on the eyes, and write, let me move my equal signs down a little bit, and we can write -1 to the 1 plus 1, A11 times the determinant of M11 plus -1 to the 1 plus 2, oops, 1 plus 2, first row, second column, A12 times the determinant of M12 plus -1 to the 1 plus 3, whoops, you probably caught it, I'll fix it, A13, I forgot the A13. Hope I didn't drive you crazy before finding that, times the determinant of M13. Okay, so let's collapse this even further. This using sigma notation. Look what's not changing in those -1 factors, -1 to the power factors. First row, 1 plus the column changes as we move that little green line through. So -1 to the 1 plus j. So we're going to be summing along j or over j. Then look at the subscripts on A's, A11, A12, A13. The row about which we're expanding indicates that the subscript on A stays that row, first row in particular. The J is changing, the column is changing, times the determinant of the M1J minor. J ranges from 1 to the number of rows or columns in the matrix. So n, I should put n there. It was 3 in our case. So 3. Okay. This is the formula for the computation of the determinant of a 3 by 3 matrix when you have an expansion about the first row. Expansion about the first row. Okay. So, let's do another example. Move my screen over. So my next example for us is to compute the following determinant. So compute the following determinant. By expansion along or about. That's interesting. I said about, and in my notes I wrote along. Row 1, the first row. So there's the determinant I'm using the alternate sort of extended absolute value bars notation. And so that we can get used to using the formula, the sum formula, let's write this out. This is the sum. J ranges from 1 to 3, and the sum would be from 1 to 4 if it were the determinant of a 4 by 4, etc., 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 etc. Okay. -1. This is expansion about the first row, so it's -1 to the 1 plus j. That 1 comes from the row along which we're expanding. That's going to be important later. A1 again from the same concept, we're expanding about the first row, but the j changes, times the determinant of the 1j of the 1j entry of A, or the 1j determinant, 1j minor of A. Okay. That didn't come out real well verbally. Okay, so that's the setup, and I'll extend little arrows to indicate where the ones are coming from, because we're expanding about the first row. Okay, so we would just expand this out. When j equals 1, I'm looking at -1 to the 1 plus 1, a1, 1, determinant of the 1, 1 minor of a, oops, plus, when j equals 2, I have -1 to the 1 plus 2, a1, 2, determinant m1, 2 minor of a, plus -1 to the 1 plus 3, a1, 3, determinant 1, 3 minor of a. Okay. Mostly this is just so we get used to this notation and stuff. Okay. So we're looking at -1 to the 1 plus 1. a1, 1 is 4, times the determinant of m1, 1. Eliminate row 1, column 1, you're left with the matrix -1, 2, -4, 0. I'm using the alternate sort of elongated absolute value bars. Oh my goodness, that's the thickest elongated absolute value bar I've ever seen. Let's see. I gotta fix this. Okay. Then next one, next term, -1 to the 1 plus 2. a1, 2 is 5. Times the determinant of the matrix whose entries are obtained by removing row 1 and column 2. So you get 0, 2, 2, 0. And finally plus -1 to the 1 plus 3. a1, 3 is 3. First row, third column. Determinant, remove first row, third column. So 0, -1, 2, -4. Okay. And I know it's torturous, so I promise I'll eliminate the computations of those 3 2x2s. So this equals, after some computation, 58. If you want to try it on, stop the video, try it on your own, that's cool. If not, that's fine. You'll be doing stuff with homework real soon. Okay, let's polish up this definition even a little more. Okay, I want to make this definition of the expansion about the first row even easier on the eyes. So here's that expansion again. It was the sum. J ranges from 1 to 3, -1 to the 1 plus j, a1, j, determinant of the 1j minor of a. What I want to do is I want to define something else. I want to help us make this notation a little easier. I want to group the -1 to the 1 plus j and the determinant of the 1j minor of a. I want to group those two together. Okay, in order to do that, I'm going to be introducing the concept of a cofactors. Okay. Okay. The cofactor of a I j is c I j, and it's defined to be that part that I wanted to lump together. It's -1 to the I plus j. In ours, it's going to be 1 plus j. In our expansion, it's going to be 1 plus j. So I plus j times the determinant of the ij element of A, or the ij, times the determinant of the ij minor of A, or the determinant of the minor of entry ij of A. I was trying to use your author's terminology, and it still bothers me. That's okay, it's just me. And I just realized in my notation for the cofactor of aij, my C looks like a small c. Your author actually uses capital C. Doesn't look that much bigger, but all right, I think you get the idea. Okay. So I can rewrite my formula for the determinant of A as the sum. J goes from 1 to 3. I'm going to combine the -1 to the 1 plus j and the determinant of the 1j minor of A to be A1j times C1j. Okay, so in doing this, I simplify the notation even further. Try to make my statement a little easier to read. There it is. Okay, and that's pretty cool. It's a nice. I think that's a nice consolidation of notation. Okay. So with the introduction of cofactors, our expansion about the first row can be referred to as something different. It can be referred to as the cofactor expansion about the first row. This is called the cofactor expansion about the first row. Okay, so just to make sure we're all in the same boat with this. This means that if I write this out, when j equals 1, I get A11, C11, j equals 2 plus A12, C12 plus j equals 3, A13, C13. And look at how simple that sum is to look at compared to the expanded version in terms of minors and so forth. Okay, all right. So that's really nice. Okay, I'm gonna circle this in red because it's a real important part of our discussion here. Okay. Our next theorem tells us that we can expand, or we can evaluate determinants by expansion about any row, or actually any column. So if I wanted to expand about, let's say, row 2, so if for example, I wanted to have an expansion about row 2, and I have no idea why I'm writing in red here. So I'm going to take that and write it in black. I have no idea why I changed it to red. Okay. TMI here. Okay. So expansion about row 2, the determinant would change, and this is the beauty of this cofactor notation. The determinant would be changed to A2j C2j. J ranges from 1 to 3. Okay, if we have a 3 by 3 matrix. Okay, so why would we want to expand about a different row? Okay, and keep in mind, way back to the first example where I looked at a determinant for you, the expansion about row 1 corresponds to the little green line that never moved in the process. So expansion about row 2 means a little green line or whatever color line you want goes through the second row, and that doesn't move. And you have 3 lines going through the 3 columns one at a time to form the sum. Okay, so let's evaluate. Let's look at an example. Let's evaluate a determinant by expansion about or along row 2. So here's the actual determinant, and then that determinant then will equal, if I expand, or rather expansioning by expanding about row 2, it's going to look like in some form, the sigma notation form, j goes from 1 to 3, a row 2 j, c row 2 j. Let's see what that looks like in terms of a sum. It looks like a, when j equals 1, 2, 1, c 2, 1, plus j equals 2. A 2, 2, c 2, 2, plus a, j equals 3, a 2, 3, c 2, 3. Okay, and that common 2 in the first entry of the subscripts corresponds to having that little green line, that solid green line that never moves through the through the second row, expansion about the second row. Why would I do that? Well, let's keep moving. Let's keep moving with this. A21, that's where the little vertical green line would go through the first row and intersect at A21, which is 0 times C21, plus A22, which is negative 1 C22, plus A23, 2 times C23. And the answer to why we would choose to expand about the second row is in that line I just wrote. Notice the coefficient of C21. Notice the coefficient of C21 is 0. I never have to compute the cofactor of the matrix. I never have to compute that 2-1 cofactor. That's the key here. The idea is when we get matrices of large size or much larger than 3 by 3 matrices, we want to do as few computations as possible. Okay, so again, if you missed it, this C21, this 2-1 cofactor never has to be computed. We never have to compute this. Compute C21. Okay, and we get that fact because we're expanding about row 2, which includes that 0 entry. That's an important thing I just said. I chose the second row because it had a 0 entry in it, which means that there would be a cofactor and ultimately a determinant of a minor that I would never have to compute. Okay. Now, if this were a much larger matrix, the cofactor would involve the computation of a much larger determinant. Okay, and determinants take a lot of operations. All right. So let's move forward with this particular example. So this then becomes, if I were to keep that first term in any way, it would be 0, and the 2-1 cofactor is negative 1 to the 2 plus 1. Actually, I'm writing this backwards here according to our formula. Never mind, it's okay. So it's negative 1 to the 2 plus 1 times the determinant of the 2-1 minor of A, so I guess we should move over, plus the next entry, negative 1, times the 2-2 cofactor is negative 1 to the 2 plus 2 times the determinant of the 2, 2 minor of A plus 2 times -1 to, see the 2, 3 cofactor is -1 to the 2 plus 3 times the determinant of the 2, 3 minor of A. Okay, so that's the determinant written out in terms of minors. So, sorry about that. So this is, I don't need to compute this, so I'm not going to do it. So plus -1 times -1 to the 2 plus 2 is +1. So this is times the determinant of the 2, 2 minor of A, the 2, 2 minor of A, back to our matrix, way back to our matrix. Where is our, oh, there it is. Sorry about that, folks. The 2, 2 minor of A is going to matrix whose entries are -1, 2, 4, and 0. Sorry about this floating around here. -1, 2, 4, and 0. So there's a little video magic too for our matrix, just to remind us what it was, or our determinant. So plus, continuing on, -1 to the 2 plus 3 is -1. So -2 times the determinant of the 2, 3 minor of A. The 2, 3. Second row, third column is 3, 2, 0. Leaves us with the determinant of the matrix whose entries are 4, 5, 2, and -4. If that's not clear. So if that's not clear at all, I can put the little green lines in. 2, 3, second row, third column, 4, 5, 2, -4. Those are the entries that are left. So 4, oops, I want to go back to black. 4, 5, 2, and -4. Okay, so this again reduces our computation. This is just -1 times -1 times 0 minus 2 times 4, multiplying along diagonals, minus 2 times 4 times -4, -4 minus 5 times 2, and that gives us, let's see, what does it give us? It's supposed to give us 58. I'll go ahead and figure it out. So this is -1 times -8. Doesn't look like what I have here. Hang on a second. Yeah, I stopped the video real quick and discovered something you probably discovered, another error in my computation, that 2, 2 minor, I think, is not correct. So I'm going to fix it. And the 2, 2 minor is 4, 3, 2, 0. And I don't know why I have -1, 2, or 0. That is so bizarre. Okay, so I'll fix this. Let's see. Fix this up. Fixing up the determinant of the 2, 2 minor. The 2, 2 minor should be 4, 3, 2, 0. 4, 3, 2, 0. And I think the last one is okay. So that changes our work here. 4 times 0, 3 times 2. 4 times 0, 3 times 2. Changes it to -1 times -6. That's better. And I think my last minor computation is correct. So let's see. We get -2 times -16. Take away 10 more is -26. So this is 6 plus 52, pages, 58. That agrees with what I had on my notes, so obviously it should be okay. That was a joke, but no, I think this is okay. All right, so there's the cofactor expansion about the second row. So the major theorem that I was referring to before I started this example, in your textbook, it's Theorem 1.16. Theorem 1.16. It has two parts. I'll say part 1. We can expand about any row. We can expand about any row, as long as our matrix has the correct size and contains that row. Okay, so the expansion, the cofactor expansion about row I, Remember, if it was row 1, we got the sum A1J C1J. J goes from 1 to n, which was 3 before, n was 3 before. If it was row 2, it was A2J C2J. J goes from 1 to n. So it seems reasonable that the determinant of A, if we have an n by n matrix, expansion about row I should be the sum Aij Cij, where J ranges from 1 to the number of rows or columns in our matrix. Okay. This is the expansion about the about row I, not the third row. Okay. We can also expand about any column. So that's what part 2 says. Part 2, let's say it that way. Part 2, we can expand about any column. Let's see what that would look like in an example without jumping to a formula, although you can probably guess what the formula is going to look like. Let's look at an example. Let's evaluate the determinant let's see, by expansion about column 3 in the following matrix, following determinant. The determinant is the determinant of the matrix whose entries are column or row-wise 1, 2, 3, 4, 5, 0, 6, 7, 0. So why did I choose column 3? I think you get it, because column 3 has zeros in it. In fact, it has 2 zeros in it. That means there are going to be some cofactors and ultimately then determinants of minors that I'm not going to have to compute. Okay, so let's see what that would actually look like using the green line sort of method, and then we'll write the formula out. Okay, so third column, imagine now we have a line that's going to be fixed through the third column. Okay, and then you're going to have lines, then horizontal lines going through that are going to change. They're going to move. So along the first row, the intersection then of those two lines is at 3, and then times the 1/3 3 cofactor of the matrix. Okay, then we're going to move that little line, that little horizontal line, through the second row. So the vertical line stays fixed. The fixed line corresponds to the column or row about which we're expanding. We're expanding about the third column so that it stays fixed through the third column. Okay, so second line then intersects at 0. That was the whole idea. Then we multiply by the, well, let's say we're in the second row and third column. And finally, we move that little green line so that it's now through the third row. Intersection is at 0. Again, that's the reason we chose the third column. Times, we're in the third row and third column, the 33 cofactor of matrix. Okay, and look at what kind of shrinking the number of operations that occurs. The 1, 3 cofactor is -1 to the 1 plus 3 times the determinant of the 1, 3 minor of the matrix, or 3 times -1 to the 1 plus 3 times the determinant of the matrix whose entries are 1, 2, 4, and 5. Let's see. No, 4, 5, 6, and 7. Sorry about that. My goodness, I'm doing it again. 1, first row, third. Okay, yeah. The problem is I left that green line through the third row, and I should have done that. Because we're looking at the 1, 3 minor, so first, there's a green line back through the first row. There we are. Sorry about that. Okay, so 4, 5, 6, 7. 6, 7. This cleans it up. Okay, and this is simple. This is just 3 times 1 times 28, 4 times 7, minus 5 times 6 is 30. 28 minus 30 is -2, times 3 is -6. Okay, so this is how you compute the determinant by expansion about column 3. So what would it generally look like then to expand about, what the formula look like to expand to the cofactor expansion about column J, column J. Okay, if you didn't follow what I just said, just to make things really complete, expansion about row I. Expansion about, we already discussed this, about row I is the sum A, I, J, C, I, J, where the sum occurs along J, or through the J's. J goes from 1 to n. Okay, so the expansion about column 3, look at our column 3, was the determinant of A equals the sum. And notice that the sum, in the sum, the index, the lower index, the first number in the lower index changed. So we're not summing along J's now, we're summing along I's. I, the row, changes from 1 to 3. A, I, 3, C, I, 3. So the expansion about column J then looks like the determinant of A equals the sum. I ranges, we're summing along the rows. I ranges from 1 to the number of rows or columns in the matrix. A, I, J is fixed through the problem. C, I, J. So you can compare the two master formulas for expansion about row I and column J. For expansion about row I, the I stays fixed, and we sum over the J's. With the expansion about the columns stays fixed, J, and we expand along the rows. That's the only difference in the two formulas. One sums along J's, one sums along I's, through the I's. Okay. We keep fixed either the row or the column that we're expanding about. Okay, so let's take a look at evaluating the determinant of a much larger matrix and see how this stuff comes into play. So here's an example. Oops. Let's go back to, okay, here's our example. Evaluate the following determinant. And we could just start this by evaluating the determinant about the first row, just like we were taught in not in elementary algebra, intermediate algebra, algebra 2. Now, the idea, though, is to eliminate or minimize the number of computations that need to be done, because these determinants, the bigger the determinant, the more the increase in the number of operations occurs is tremendous. This is just a 4x4. But to evaluate a 4x4 determinant, we really, by the cofactor expansion, reduce it to evaluating 3x3 determinants. Okay, let me say that again. If we expanded about the first row, we would need to evaluate 3x3 determinants in that sum. And each of those 3x3 determinants requires the evaluation of 3 2x2 determinants, okay, and so forth. So you can imagine that if we were evaluating a 25x25 determinant, that the number of operations, the total number of operations would be staggering. Just look in the first iteration. If we were evaluating a 25x25 determinant, expansion about the first row, we would have to evaluate 24x24 determinants, and each of those 24x24 determinants involves, I think you get the idea. The total number of operations is absolutely staggering. So, bottom line is, it would be nice to choose the row or column in the original matrix that has the biggest number of zeros in it. And your eye probably went directly towards the third column. So the idea is to expand about a row or column that has the greatest number of zeros in it. So we're going to first expand. We're going to first of all, we're going to expand about column 3. Okay, so this determinant then becomes, well, we're expanding about the column. The column stays fixed, so it's A, I, 3, C, I, 3. I ranges from 1 to what? 4. Okay. Well, you know, this kind of this in the sigma notation, it kind of hides what's really going on here. So this is really written out. It's A13C13 plus A23C23 plus A33C33 plus A43C43. Okay. Now notice that in column 3, there's only one non-zero entry. This is 0 times C13. A23 is 0. 0 times C23. A33 is the only non-zero entry in that column. See, that was the whole idea behind choosing the selection of the third column. Plus 0 times C43. 3 of those cofactors need not be expanded or evaluated, and each of those cofactors would involve a 3x3 determinant of a 3x3 matrix. So this now simply becomes negative 2 times C33, or negative 2 times negative 1 to the 3 plus 3 times the determinant of the 3 minor of this matrix. So let's write this out. So this becomes negative 2 times the determinant of what? The 3 minor. Let's get a horizontal line through row 3. The 3 minor now is the 3x3 matrix whose entries are 7, negative 3, and 4. Let me write this out. 7, oops. Negative 3 and 4, 2 more rows. 0, 1, and 3. 0, 1, and 3. And finally, 0, 4, and 6. 0, 4, and 6. One 3x3 determinant, as opposed to having to evaluate 4 of them. So we selected row 3 because it had the largest number of zeros in it. Now, we have to evaluate this last 3x3 determinant, or determinant of a 3x3 matrix. But we don't have to expand it about column 3 just because we expanded the original matrix, or a determinant about column 3. What should we do now? We should now expand about the first column. It has zeros in it. So now expand about column 1. Okay, and a computer can do this very, very quickly. A computer can, at each stage, a computer can search for the column or row with the largest number of zeros and evaluate the resulting determinant about that row or column at each stage, thereby minimizing, or in some case reducing at least, the number of operations required for the determinant by a tremendous amount, potentially. Okay, so let's do that. So we're going to expand about the first column. So it's negative 2 times about the first column. It's going to look like the sum I first column, C I first column. I goes from 1 to now 3. Okay, or written out, it looks like A11 C11 plus A21 C21 plus A31 C31. But only A11 is a non-zero number. Only A11 is a non-zero entry. So this is -2 times 7 C11 plus 0 C21 plus 0 C31. Okay. Or -2 times 7 times -1 to the 1 plus 1 times the determinant of the 1, 1 minor of our matrix now. Okay, super simple here. So this is -14. The 1, 1 minor, delete first row and first column. You're left with 1, 3, 4, and 6. 1, 3, 4, and 6. Using that alternate notation for the determinant of the absolute value bars or whatever. So this is nothing more than 6 minus 12. 1 times 6 minus 3 times 4. -14 times -6, which is, let's see, positive 84. Okay, so the idea is to compute determinants efficiently. Okay. Okay. Let's look at a couple of theorems that involve or having to do with computation of determinants. These theorems are called corollaries. If you're not familiar with the term corollary, it's a very simple idea. A corollary is an actual theorem itself that's an immediate result of a previous theorem. Okay, so as a result of a previous theorem, we get these two sort of sub-theorems, which these are called corollaries. So corollary 1.17, I think you'll get this first one right away. Suppose you have a matrix that has a row or a column entirely of zeros. Then what's the value of the determinant? Again, suppose you have the first row of a determinant. Big determinant or small determinant, doesn't matter. The first row of the determinant is all zeros. What is the value of the determinant? It's simple. It's 0. If you have the first row is entirely of zeros, then expand about the first row. Then each of the coefficients in the determinant are 0. So that's the first of these corollaries. So if A has a 0 row or column, or both, I guess, then the determinant, sorry about that, of A is 0. Okay. The proof is immediate. Simply expand about the 0 row or column and you get the result. The next one, the next corollary, has to do with the determinants of triangular matrices. Remember, we have concept of upper triangular, lower triangular. The determinant of a triangular matrix is the product of its diagonal entries. We'll prove that. The determinant of a triangular matrix, either upper triangular or lower triangular, of a triangular matrix is the product of the, or let's say the product of its diagonal entries. Just means if you have an upper or lower triangular matrix, just multiply the entries on the diagonal, the main diagonal, and you get the value of the determinant. Easy to see. Let's take a look. Let's find the determinant of, say, A11, 0, 0, lower triangular here. So 0, 0, zeros in the first row except for the first entry. Then let's say A21, A22, and then zeros. And let's do one more. A23. Oh, no. Sorry about that. Get rid of that. The next entry would be, or the next row would be third row, so A31, A32, A33, then zeros, and continuing on. So we're looking at the last row would be, suppose we have an n by n matrix, a n1, a n2, and a n is non-zero potentially here. A n3 ... Okay, here we go. So we're looking at a lower, the most general n by n lower triangular matrix. Let's expand about row 1. Row 1. Okay, so what are we going to get? If we expand about row 1, we're going to get A11, C11. That's it. Okay, well, let's see what it's going to look like. It looks like A11 times -1 to the 1 plus 1 times the determinant of the 1, 1 minor of A. If you let's do a little green line thing. If you put a horizontal green line through the first row and through the first column, you're left with the n-1 by n-1 matrix, A22, 0, 0, ... 0, A32, A33, zeros, ... all the way up to zeros, all the way down to AN2, AN3, ... up to ANN. Now what do? We do it again. We expand about row 1. We keep expanding about row 1. So we're going to get A11, -1 to the 1 plus 1 is -1, so we're going to get A22, C22. Okay, and we continue this. A22, C22 is A22 times -1 to the 2 plus 2 times A33, zeros, zeros, all the way up to ANN. Okay, and we continue this process, expand now about the first row. So we get A11, A22, expanding about the first row, A33, then expand that about the first row, A44, ... all the way up to, oh, not plus, times, oops, that's not an eraser, all the way up to A and N. So this is really not a complete proof, but you get the idea. We keep expanding about the first row, expand about the row's first row. The only thing that's left is the product of the entries along the diagonal. Okay. So the problem is not every matrix is a triangular matrix. So it would be nice to reduce the number of operations required to evaluate a determinant. It would be nice if we could somehow transform our matrix. Remember, it's not necessarily an upper triangular, lower triangle matrix. We could somehow transform our matrix into one that's a triangular matrix, and then just simply multiply along the diagonal. That's ultimately where we're headed. If you miss that, we're ultimately headed in this segment of our lecture in a procedure that says that if you want to minimize the number of operations necessary to compute the value of a determinant, perform certain operations, simple operations that don't take a lot of operations, a lot of computations, to transform your matrix first into a triangular matrix, and then to end the process, just multiply along the resulting main diagonal. Okay, so along those lines, let's take a look at some more theory. Our next theorem is Theorem 1.19 from your textbook. Okay. The determinant of A transpose is the same thing as the determinant of A. That's kind of neat. It's also easy to see. 1, 2, 3, 4. That determinant is 1 times 4 minus 2 times 3. Or 4 minus 6, which is negative 2. Okay, what if we take the transpose of the original matrix? So let's look at 1, 2, 3, 4 column-wise and check the transpose. This is simply 1 times 4 again, minus 3 times 2. The same thing. So it's kind of easy to see with a 2 by 2. But it's generally true. If you take the determinant of a matrix, you don't affect the value of it, the determinant of that matrix. Okay. Okay. Well, how about if we interchange rows? If we don't interchange rows and columns, that's how we get a determinant. But we interchange a particular row. So now let's take a look at 1, 2, 3, 4. Okay, which we already computed. It's just 1 times 4 minus 2 times 3, whatever. Now suppose we interchange the two rows, 3, 4, 1, 2. The new determinant is 3 times 2 minus 4 times 1. This is just a reversal of the sum. This is the first is 4 minus 6, which is negative 2. The second is 6 minus 4, which is positive 2. So this sort of gives us a beginning to Theorem 1.20. Theorem 1.20 is a big one. Theorem 1.20 is kind of involved. So let's say let A equal the matrix whose entries are Aij. Let this be an n by n matrix. So it's a square matrix. Okay. So first, if you form a new matrix by interchanging any two rows of A, okay, so if B is a matrix obtained by switching, spelling looks terrible there, any two rows of A, then what does that do to the determinant? The determinant of the resulting matrix of B is then the opposite of the determinant of A. If you switch any two rows, you introduce a minus sign. You change the value of the determinant by a minus. So what happens if you switch any two rows and then you switch any two other rows? You get back to the value of the original determinant. Every time you switch two rows, you introduce a minus sign as a factor, minus one as a factor. Okay. So the next part of the theorem says, or answers the question, what happens when you multiply a row by a constant? Okay. So let's motivate that. Let's motivate number 2 before we state it. Let's motivate number 2 with an example. Let's say, let's do this. Let's let A equal the matrix whose entries are 1, 2, 3, and 4. And let's let B be the matrix that you get by multiplying row 2 by pi. 1, 2, 3 pi, 4 pi. What's the determinant of B? Determinant of B is 1 times 4 pi minus 2 times 3 pi, or 4 pi minus 6 pi, which is negative 2 pi. Well, we already know the determinant of A. We've seen it a few times. We can look at it again. The determinant of A is 1 times 4 minus 2 times 3, which is 4 take away 6, which is negative 2. So if I multiply a row, the second row by pi, that changes the value of the determinant by a factor of pi. Okay? In other words, the determinant of B is pi times the determinant of A. Okay. It's essentially saying that here's the determinant of B. 1, 2, 3 pi, 4 pi. You can factor out constants from single rows, not from an entire matrix. Be careful, that's a big deal. From a single row. Okay. So let's put all this together in part 2 of the theorem. Part 2 of the theorem here. Hang on a second. Let me correct my little blunders here. Part 2 of the theorem. Part 2 of the theorem says that if a new matrix B is obtained by multiplying a row by multiplying a row by a scalar C, okay, so what B is what was obtained from A. B is obtained from A by taking just any row of A and multiplying by a scalar C. Then the determinant of B is equal to C times the determinant of A. You can factor constants out of determinants. Single rows. I'm sorry, I said that wrong. You can factor a constant out of a single row of a determinant. Okay. Okay. The third property is a little dangerous. It's a little dangerous for a reason that's going to become apparent. What happens if you perform the third of the elementary row operations that we use in Gaussian elimination? Let me be much more specific. Let's say if B is obtained by replacing a row of A by itself plus a multiple of another row then, and this is kind of neat, the determinant of B is equal to the determinant of A. So if you perform that most complicated of the elementary row operations, the value of the determinant remains the same. Okay. Let me be a little more explicit here. So this is saying that is B is obtained by, let's do this, by the elementary row operation row I plus, let's say, B row J, let me say it better, constant K row J back into row I. Okay. So if you perform that elementary row operation, then the value of the determinant is unchanged. Don't worry about proving it. That one's a little bit elaborate. I'm going to look at very carefully at this theorem, and we'll do that by looking at, let's say, a true or false question. So, for example, true or false. That's the first part. Let A be a 4 by 4 matrix. Then the determinant of 3A, 3 times the matrix, is equal to 3 times the determinant of A. And let me preface by saying that I found that most students get this wrong in the first try. A lot of students will say, oh, true, you just factor out the 3. You just said we can factor out a constant from matrices. You can factor out a constant from each row, from a single row in a matrix. If I multiply a matrix A by 3, I multiply each row by 3. So this can be fixed. This is false. This is a false statement. False, 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 false. You can factor a 3 out of a single row, but when you multiply a matrix by 3, you're multiplying the first row, the second row, the third row, and the fourth row by 3. So how could we fix this? We could correct it by saying the determinant, let's see if you can think of it, of 3A is equal to what? I can factor a 3 out of the first row, a 3 out of the second row, a 3 out of the third row, and a 3 out of the fourth row times the determinant of A. Or 3 to the fourth times the determinant of A. Okay, this is a tricky one. So B. This one's a bit more involved. And this is a very important one here. So B, performing A times row I plus B times row J back into, let's say, row I doesn't change the value of the determinant, the determinant. Yeah, let's do it that way. It looks very, very convincing. It looks like part 3 that I have of the theorem above, which I'm going to highlight in red. It looks very much like part 3. Very similar, actually, to part 3. Row I plus k times row j back into row I. A times row I plus b times row j back into row I. Unfortunately, it is false. The problem, and this is a big deal, is that this is not an elementary row operation. This is a combination of two row operations. This is a combination of multiplying row I by A, which definitely affects the value of the matrix. If you multiply a row of a matrix by a constant, you affect the value of the constant. Remember, you can factor out that constant. Okay, so this is false. This is absolutely false. So we can't combine the row operations like we did with the Gauss-Jordan and Gaussian elimination methods. We can only use that one more complicated row operation of replacing a row by the sum of itself plus a multiple of another row. Okay, we can't multiply the original row by a constant first. Okay. Final note is in this theory, all of these row operations can be replaced by the same column operations, and we have the same thing hold true. Okay, so if you can factor out a constant from columns, you can replace a column by the sum of itself and a multiple of another column without affecting the value of the matrix. And the reason for that is that it comes from the first part of the theorem that said that the determinant of the transpose is the same thing as the determinant. Okay. So why this massive theorem? Well, I told you why. Basically, the idea is to produce some sort of procedure that's very easy to program in a computer, where the computer will perform elementary row operations to the matrix to produce a triangular matrix, and then multiply the elements along the resulting diagonal, the elements along the resulting triangular matrix to get the value of the determinant. Okay, I want to show you that with an example. Okay, so let's think like a computer to evaluate this determinant. Let's use the theory that we talked about to evaluate this determinant, the determinant of this 4x4 matrix. I would like to perform elementary row operations on this matrix, the matrix involved in this determinant, until I get to an upper triangular matrix. So then I can just multiply along the main diagonal to get the value of the determinant. So I'm going to do that. So let's try to row reduce this matrix to an upper triangular matrix. So the first thing I want to eliminate or change is the entry in the second row and first column. I want to get that 2 underneath that leading 1. I want it to be 0. So I'm going to take row 2, and I'm going to subtract 2 times row 1. And that's not going to change the value of the determinant. Remember, I get to do row I plus k times row j back into row I, and I get to do that without changing the value of the determinant. So I'm also going to get rid of the 1 below that 2. I'm going to take row 3. I'm going to subtract row 1. I'm going to get rid of the 5. So in the fourth row. So I'm going to take row 4. I'm going to subtract 5 row 1s. And in the process, I'm not going to affect the value of the determinant. So this is going to be equal to the determinant of row 1 is not changing. So 1, -1, 2, and 3. Okay, I'm going to go through these operations very quickly. So I'm going to get zeros along, or for each of the entries, the rest of the entries in the first column. So the resulting remaining entries are going to be 0, 4, and if you're so inclined, you can verify that my row operations are giving the correct numbers. I verified this a few years ago, so it's okay. I hope. I think I did. No, I did. Oh, that's wrong. That's 1. 0, 3, 1, and negative 3. 0, 8, negative 4, and negative 16. Okay, so this is not upper triangular yet. We still have 3 problem numbers. 3, 8, and negative 4 need to be changed to zeros. So let's concentrate on the numbers below the 4, the 4 in the second row. I want to have zeros below that 4. All right, so let's do that. Well, to do that, I'm going to factor out the 4 from the second row. So remember, we can factor out constants from rows or columns. So I'm going to factor out a 4 from the second row. I'm going to leave the first row alone. Factor a 4 out from the second row. And just for now, I'm going to leave the third and fourth rows alone. They will be changed soon. Now I'm going to get zeros below the leading one in the second row. In order to do that, I'm going to take row 3, and I'm going to subtract 3 row 2s. Then I'm going to take row 4 with that 8 in it. Then I'm going to subtract 8 row 2s without changing the value of the determinant. Okay, so here's the resulting matrix. I'm not doing anything with the first row. I'm not doing anything with the second row. I'm changing the third and fourth rows, and the results, which you can check on your own if you'd like. Just stop the video if you want. 0, 0. What do we get? Let's see. 4 and negative 8. And we're almost there. It's almost upper triangular, if there can be such a thing as almost upper triangular. Okay, so what I want to do is I want to get 0 before that first entry of 4 in row 3. So I'm going to do a row operation on that. I'm going to take row 4, and I'm going to subtract row 3. And that should pretty much get us to the end of this. I'm not doing anything with the first row. I'm not doing anything with the second row. I'm not doing anything with the third row. I'm taking row 4 minus row 3. And that resulting matrix is upper triangular. To get the value of the determinant of an upper or lower triangular matrix, you simply multiply along the main diagonal. So you get 4 times negative 32, which is negative 128. Notice there was no need for a cofactor expansion of any sort. All I had to do was to transform through elementary row operations, which, by the way, don't require a lot of computations ever. to create an upper triangular matrix. Okay. Well, that ends section 1.5. We still need to take a look at 1.6, which is, it's going to go fairly quickly. The thing that will take the longest in this is just a very brief review of Kramer's rule. I'm not going to spend a lot of time on even Kramer's rule. So what I'm going to do to finish up this video segment is take a look at section 1.6. So let's get through it. Most of this I'm going to state without proof. If you're a math major, you will very, very likely take this course all over again as a course specifically for math majors, and you'll do a lot more proof, formal proofs. So Theorem 1.21. This one we're going to use, this theorem we're going to use extremely often in our future. So A is non-singular if and only if and only if the determinant of A is not 0. So again, we go back to invertible matrices. They're going to play a big part in our future. A has an inverse. A is non-singular if and only if this determinant is not 0. So if you figure out the determinant of a matrix is not 0, it has an inverse. And conversely, if you figure out somehow that a matrix is non-singular, then you don't have to evaluate a determinant. You could tell that the determinant is not 0. Okay, next theorem. Theorem 1.24. If you want the determinant of the product of two matrices, it turns out you never have to multiply the matrices together to get it. The determinant of AB is the same thing as the determinant of A times the determinant of B. That's pretty neat. To find a determinant of the product of these two matrices, A and B, you never have to multiply A times B. Just multiply the determinants, the individual determinants together. That's amazing. Okay. Corollary 1.25. The determinant, if you want the determinant of the inverse, you never have to find the inverse. It's simply 1 over the determinant of A. This is amazing. Finding the inverse there's a lot of operations to find the inverse. So, but if you want a determinant of the inverse, you don't have to find the inverse first. You just find a determinant of A and then find its reciprocal. But what if the determinant of A is 0? Then that makes this formula not legitimate. Well, if you're finding the determinant of A inverse, it's implied there that A is non-singular. You can't find the determinant of A inverse unless A inverse exists. But the first theorem we just looked at a few seconds ago says that if your matrix is non-singular, then the determinant is not 0. Okay, the proof of this one's very simple. You should see it. Proof of this one's is not difficult at all. See, the fact is that the determinant of the identity matrix is 1. Why is that true? The identity matrix is like the ultimate triangular matrix. It's both upper and lower triangular. Not only that, the elements along its diagonal are 1. So the determinant of the identity matrix we get just by multiplying 1 times 1 times 1 n times for an n by n identity matrix. But we know that the identity is the result of multiplying A by the inverse. But we know the determinant of AB is the determinant of A times the determinant of B, the second matrix. It's over. It's over. Let's just divide both sides by the determinant of A. Okay, QED. Multiply both sides of that equation, or divide both sides by the equation by determinant of A. Okay, and let's see. You have my permission to skip corollary 1.26 and 1.27. Corollaries 1.6, 1.27. Okay. So we end this video segment with a review of Kramer's rule. Your author calls Kramer's rule Theorem 1.28. Kramer's rule. It's assumed that you know what Kramer's rule is, because you're supposed to have had it, but I'll state it for us here. So here's Kramer's rule. Theorem 1.28, called Kramer's rule. Kramer's rule is for very special systems. First, the system has to have the same number of equations as unknowns. So we have n equations and n unknowns. Suppose ax equals b is a system of n linear equations in n unknowns, satisfying the determinant of the coefficients is not zero. The determinant is not zero of the coefficients. Okay, then we start constructing those special matrices in Kramer's rule. Let A sub k be obtained by taking the coefficient matrix A and taking out the number k column. Remove the kth column and place the kth column by the constants in the system. Then, as you most likely learned in Algebra 2, the unique solution is x1 is the determinant of a1 over the determinant of a, x2 is the determinant of a2 over the determinant of a, all the way up to the last variable, the determinant of a sub n or the determinant of a. Okay, I want to do one very simple example for you. So solve by Kramer's rule. I'm going to make up a system right off the top of my head. So the system is going to be 3x minus 4y equals 7. And x plus 2y equals negative 1. I want to solve that system by using Kramer's rule. Okay. It's definitely in the right form for a system to be using Kramer's rule. We can rewrite the system in matrix form, ax equals b. Okay. Okay, so A is the coefficient matrix. The determinant of A needs to be non-zero, so we should check that. So this is 3 times 2 minus negative 4 times 1, or 6 plus 4, which is 10, and it's definitely not 0. So Kramer's rule will work here. Okay, so A1 is the matrix that we obtain by taking the coefficient matrix and take the first column out and put in the constants from the system, 7 and negative 1. So we leave every other column alone. There's only one other column. A2 we get by removing the second column, negative 4 and 2, from the coefficient matrix and replacing the constants for the system. But we leave the first column alone. Okay. So then we compute, we need the determinant of A1. That's 7 times 2 minus negative 1 times negative 4, which is 14 minus 4, and that's 10. Also, the determinant of A2 is 3 times negative 1 minus 7 times 1, which is negative 3, take away 7, which is negative 10. Then it's over. Kramer's rule says that x equals the determinant of A1 over the determinant of A which is, oh my goodness, that made this system have an easy solution. Determinant of A1 is 10. Determinant of A is also 10. I did not intend the solution to be so simple. Usually when I make up problems, the solutions turn out to be really strange. Oh well. Who would have thought? Determinant of A2 is negative 10. Determinant of A is positive 10. So the solution is x equals 1, y equals negative 1. Okay. And that brings us to the end of a very long video segment. We just finished covering sections 1.5 and 1.6. And I welcome you to dig into homework as soon as you can. And as usual, I'm looking forward to talking with you all again soon.